Materials like steel that have a pronounced linear elastic region can be characterized as Hookean materials and follow Hooke's law. So we could say stress equals some constant E times strain, where E is the slope of the linear portion of the stress strain curve. This slope we often call, the E value we call Young's modulus. So Hooke was a scientist, I suppose. Robert Hooke in the 1600s, 1700s, a contemporary of Newton. The two didn't really get along, but Hooke investigated a number of things, often through the encouragement of the Royal Society in England, where he was a member of. But he investigated the elastic properties of different metals in wood and stone, bones, sinew, other things. So, for example, steel has a value of E of around 30,000 KSI, which is like 200 gigapascals, and aluminum is has an E value of 10,600 KSI or 70 gigapascals, and wood is 1,600 KSI or 11 gigapascals. We can often characterize steel, even though it's made up of a crystalline structure, different types of crystalline structures depending on the steel. But we can on a larger scale, we can model it as though it's a homogeneous material, and model it as an isotropic material, which means it has the same properties in all directions. And with isotropic materials, you need two material properties essentially to characterize it. We're going to use E as one of those material properties, and a material property called nu, which is the Poisson ratio. Poisson's ratio is simply defined, we use the Greek letter nu, as the negative of the lateral strain divided by the axial strain. And what does that mean? What does that mean? Say you have a material here and you're going to load it in tension, then what ends up happening is you let's keep this the same. So if the gray box here is the original size of the material, and then you pull on it, laterally you elongate it, but or rather axially you elongate it, and then it shrinks in the lateral direction by this much here and say this much here. So that's why you use the negative sign. So for example, let's say you have a prismatic bar here with a circular cross section of length 3 meters, and let's say you load it with 85 kilonewtons. Let's find the lateral strain if nu equals 1/3. So the lateral strain equals, due to the relationship above, equals minus nu times the axial strain or the longitudinal strain. So we can use Hooke's law to figure out what our strain is. And that axial strain is our stress over our Young's modulus for this material. And this material is aluminum, and let's go with 70 gigapascals as E for that. So for the stress, we have 85,000 newtons divided by pi r squared. And for r in this, let's say that the radius is given as 30 millimeters. So that's our stress, our axial stress. Let's divide that by 70 gigapascals. And we get a strain of 0.004294. And that means our lateral strain is going to equal, again, minus nu times our longitudinal strain we just calculated, or minus 1/3 times 0.004294. And our answer is a negative 0.001429. Now, we can relate our Poisson ratio to stress and strain if we look at volume change. Suppose I have a chunk of material initially this size, and let's define this as the x-axis, this is the y-axis, and this as a z-axis, three-dimensional block. Then initially I have lengths of sides equal to A1, B1, and C1. So then my volume or rather my initial volume is A1 times B1 times C1. And let me redraw this so that the red lines are essentially this original size of the block here. And when I pull it, it's going to stretch in the direction I pull. Imagine that this is the surface of the I guess this is the z direction. I've changed that too. But the ZY plane is attached to the wall here, and the XY plane, this far edge of the rectangle, just slides along it. So we're shrinking laterally the rectangle and extending it in the longitudinal sense along the x-axis. So the change in length here is just the original length A1 times the longitudinal strain. Then the amount I shrink in the C direction, so is C minus C1V, so it's in actually the Z direction, but side C1 shrinks by minus C1 nu epsilon. And then along the original B1 length, we shrink by, so it's this value here, we shrink by a value of minus B1 nu epsilon, the longitudinal strain. So I'm relating to the longitudinal strain to nu of the nu times the longitudinal strain to the lateral, or I guess I shouldn't call it longitudinal, I should call it axial, so there's no confusion. So our final volume, or the volume of the orange area, is going to be A1 times 1 plus the axial strain times B1, 1 minus nu of this, times C1, 1 minus nu of that. If you multiply this out, you're going to get some higher order terms in strain, and we want to look at small strains, so we're going to eliminate the higher order terms, and I'm just going to give you what the result is. So in summary, if you expand out the final volume, this orange area, you're going to get a bunch of higher order terms, and the lower order terms, we're going to eliminate all the higher order terms, and we can simplify that with this relationship right here. So I want to look at the change in volume over the original volume, and I'm going to call this E, which is the dilatation. Another word for that. Okay, I'm going to take this final volume here and subtract off the initial volume to get a delta V, and then divide it by the initial volume. And this is our dilatation again, and this leaves us with our strain times 1 minus 2 nu. Since the A1, B1, C1s cancel out. So our change in volume over the original volume can be represented, can be related then to the strain and our Poisson ratio. This means we can write this with Young's modulus as sigma over E is also 1 minus 2 nu.